Welcome to the walkthrough for Assignment 2A for the Image Crawler Stream app. The purpose of the first part of this two-part assignment is to deepen your experience using Java's functional programming features and their integration with Java sequential streams. In particular, in this assignment, you'll develop an app that uses Java sequential streams to obtain, transform, and store images. The code you write for this assignment has a GUI and runs as an Android app. Please feel free to use this app to help debug your solution. The following resources may be helpful in completing this assignment. There's detailed coverage of Java sequential streams in weeks 4 and 5 in our course website. There's also good overviews of Java streams at these links, and I highly recommend you get the book Modern Java in Action to learn more about Java streams programming. Before you complete the initial submission of Assignment 2A, you'll need to do the following. Complete your implementation of Assignment 1B, taking into account my review comments. In particular, it's important that your unsynchronized array implementation works properly since it's used throughout the app in this assignment. Please come to office hours if you have any remaining questions about your Assignment 1 solution. As always, the Image Crawler app is packaged as a project using the latest version of Android Studio. This app is written in both Kotlin and Java and demonstrates many very interesting Android capabilities. For the purpose of Assignment 2A, however, you only need to be aware of the following directories: the Image Crawler Utils directory and the Image Crawler Crawlers directory, which contains the skeletons you'll need to fill in, as we'll talk about shortly. There's also the Image Crawler Source Test directory, which is a set of unit tests that exercise the features you're implementing for this assignment, and we use these to evaluate whether you're correctly satisfying this assignment's requirements. Finally, there's also the Android Source Android Test Java Assignment Tests, which is an Android Studio instrumentation test that runs your app automatically. To compile all this code, you'll need to use the provided Android Studio project. As always, you can run this project by clicking on the green Run App button in the Android Studio IDE, which should automatically select an emulator to run, assuming you've created one already. The minimum API for the app is Android version 29, so you'll need to select an emulator that uses API at least 29 or 30. Naturally, if you haven't created one yet, you can create it by using the AVD Manager button in the Android Studio IDE. In this first part of the assignment, you'll complete the implementation of an image crawler class in the image crawler crawlers sequential streams crawler.java file. This file is used to obtain and store images. The class in this file uses Java sequential streams to perform an image crawl starting from a given root URI. Depending on the parameters used to run the tests, images from HTML pages reachable from the root URI are either downloaded from a remote web server or read from the local file system, and the final transformed results are stored in files on your local file system. The bulk of the code for this app is provided in the skeletons. In fact, I've provided you with a complete solution using Java 7 object-oriented features in the image crawler crawlers sequential loops crawler.java file. Your goal is to convert this Java 7-based class to the modern Java sequential streams crawler class that uses the Java sequential streams capabilities. In this assignment, undergrad students have to do the following. You have to implement the key methods in the Splitterator interface, in the image crawler utils array Splitterator.java class. This was done by graduate students in Assignment 1B. Undergrads will need these methods for Assignment 2B, so now is a good time to implement them. Likewise, grad students, or students who are taking this class for graduate credit, must do the following additional work. You have to implement the Image Crawler Utils Synchronized Array class, which will then be used in Assignment 2B's Array Collector class, which is not included in this 2A assignment. Undergrad students can ignore the Synchronized Array class. As we've done in earlier assignments, your solution should use no loops or if-else statements in this assignment, and instead you should use Java sequential stream aggregate operations, as we've been covering in the lectures. Skeleton code for this assignment is available in my GitHub account in the normal location. Now that you've set up your GitLab account, you can pull this code into your repository, read through it carefully, and then complete the to-do markers. Undergrad students should implement the code with the to-do, graduates 1B, undergraduates 2A tags, whereas students taking the class for grad credit should already have completed the to-dos for Assignment 1B. There's a set of unit tests in the image crawler source test Java folder, and they're used to provide a way to increase your confidence and our confidence that your implementation works as expected. As always, you'll need to use Android Studio to run these tests on your computer as described at this link. And be aware, as is always the case, testing only demonstrates the presence of bugs, but not their absence. So don't rely solely on the JUnit test to detect problems in your code. Moreover, we're likely to improve the tests between releases of different versions of the assignment as I discover more problems that arise with frequently made mistakes. Assignment 2A is more complicated than Assignment 1, and it's designed to deepen your experience developing apps using Java's functional programming features and its sequential streams framework. In particular, the skeletons and unit tests are more extensive, though you don't need to understand them all in order to complete your solution. Just focus on the areas where I ask you to do the to-do tags. Therefore, please start early and ask questions in class, come to office hours, and also post on the discussions forums to ensure that you complete this assignment successfully. Now that we've walked through the specification for Assignment 2A, let's start taking a look at the skeletons, beginning with the Array Splitterator class. This class was implemented by graduate students in Assignment 1B. An undergrad should implement it now in Assignment 2A. A splitterator is a mechanism provided in modern Java that's a generalization of the Java iterator. In particular, it's used to partition and iterate through sequential streams and parallel streams. We'll focus primarily on the sequential streams in Assignment 2A and then parallel streams in Assignment 2B, but we'll implement the splitterator to cover both cases. As you can see, the Array Splitterator class extends Splitterator's abstract splitterator, which is a helper class that overrides a bunch of the methods so you don't have to fill them all in yourself. You begin by defining several fields that are necessary to implement the Array Splitterator, beginning with a reference to the array that will be traversed and/or partitioned. You'll also provide an index that will be modified by the try-advance and try-split methods we'll talk about below. It keeps track of where we are in the splitteration, or the iteration, if you will. And then finally, there's another field that keeps track of one past the end of the splitterator range. So for example, if you had, say, an array of 10 elements, then the end would point at 10, which is one past the end. Of course, the end is element 9 because it goes from 0 to 9. Don't get confused by the one past the end description. It's really just essentially the size of the underlying range that you're working on. The constructor for Array Splitterator, of course, will take in the various parameters, the array, the origin, and the end, and update the corresponding fields. That's pretty obvious. And then there's also some other code I provided here that initializes the abstract splitterator superclass with various fields indicating the size of the array that we're going to be splitterating over, indicating that we want to have an ordered, sized, and subsize splitterator in terms of its characteristics or its attributes. Let's take a look at the two methods that you have to implement. The first one is called try-advance, and this is used by the Java Streams framework when it needs to figure out which element to get next in the splitteration. Try-advance is basically a combination of the hasNext and next methods you find on Java Iterator, in the sense that it both will try to advance and it'll also return a value that will indicate whether it was successful or not. In this particular case, you're going to have to check to see if there's any elements left in the splitterator's range. If the answer is no, if you're all done, you return false, indicating don't try to advance. Whereas if there are elements left over, you will go ahead and consume one into the consumer action by accepting it into the action, and then you'll return true, indicating it's worth letting the framework try to advance it again. Try-split is used for parallel streams in order to be able to take a range and split it in half, and then be able to do parallel processing on each of the halves independently of each other by throwing them into the common fork join pool. If you watch the videos, it'll talk more about how the try-split method works and how it breaks things up into chunks and how those chunks are allocated and applied in the context of the common fork join pool. For right now, we don't have to know those details, however, in order to implement try-split. What try-split will do is first check to see whether or not there's any elements left, and you know that if the range is greater than 1. If the range is equal to 1, you want try-split to return null, indicating that it can't be split any further because it's reached its smallest atomic size. In contrast, if the range is greater than 1, then you need to go ahead and find the midpoint which you can identify by adding the low and the high and then dividing by 2. And then you want to go ahead and create a new array splitterator that will cover the first half from the low range to the midpoint, and that's what gets returned. And then you'll update the index to indicate that that will be the new starting point. And the index, of course, will be set to mid, and you'll go from mid to the end as the range for what remains in this object. So sometimes we talk about this as creating a new left-hand side and returning that, which covers the first half of the range, and then updating this object to become the new right-hand side, which will be from the middle to the end. It's a little subtle getting that logic right, so be careful with it. It's not really too hard. The code is pretty simple, but it sometimes can cause some confusion. And make sure you run the unit test, which should indicate whether or not you've done it correctly. Now, assuming that you're taking the class for grad credit, there's another class that you have to implement, and this is called Synchronized Array. Synchronized Array actually doesn't get used in Assignment 2A, but it will get used for the grad students in Assignment 2B. So we might as well go ahead and implement it now just to give you something additional to do to differentiate the undergrads from the grads. Synchronized Array is essentially a variant of the array interface. It's an implementation of the array interface that is got synchronized methods. So different threads can be calling into the synchronized array simultaneously without having to worry about race conditions and memory visibility issues and ordering issues or other types of corruptions and hazards that arise if you have multiple threads manipulating shared mutable state. Now, keep in mind the unsynchronized array does not have these mechanisms. They don't have synchronizers. So you can only use it within a single thread of control. And we'll talk more about that when we talk about so-called non-concurrent collectors later in the class. But for right now, you just have to focus on implementing the synchronized array. And what you'll do here is you'll start by defining some fields, and I'll give you a hint. You're going to want to essentially have a reference to the unsynchronized array that will be passed in as a parameter to one of the constructors that takes the array reference, which is named as unsynchronized array. So the constructors are very simple, but you'll have to allocate things properly or pass them in and use them properly. And then for all the methods that you see below here that are not constructors, so for everything that's not synchronized array, which is the constructor, you're going to have to put in the appropriate synchronizing mechanisms in there. And what I suggest that you do is use synchronized statements, which uses the synchronized Java keyword in conjunction with, typically with this. There's other ways to do it as well, but the easiest way to do it is to synchronize on this. And so what you'll basically do here is you'll implement effectively the parameterized synchronization pattern, or what's sometimes called the decorator pattern, where what you're going to do is decorate the call to the unsynchronized array by wrapping it in a synchronized statement that acquires the lock, the intrinsic lock, on the way into the method, then goes ahead and forwards the corresponding method on the unsynchronized array that you've declared as a field in synchronized array. And then when the closed curly brace gets hit, that will be handled by the underlying Java runtime system as releasing that intrinsic lock. And so you'll basically have to do this for all the methods in this class. So you actually don't end up replicating the logic at all. You don't end up duplicating any of the code that you wrote for unsynchronized array. You end up decorating it and then using the synchronized statements that Java provides in order to give you the various implementation elements here. So take a look at this. If you have any questions, please feel free to come to office hours and ask about that. But you'll see it's actually really quite simple to do all this stuff. You just have to make sure that you do it properly with the right decoration mechanisms that are involved. So that's essentially what you'll have to do for the array splitterator if you're an undergrad and synchronized array if you're a grad student. Let's now turn our attention over to the crawlers folder. And you can see here, there's an implementation that I give you out of the box called Sequential Loops Crawler. And this is an implementation that implements all the logic using for loops. And it kind of gives you a hint as to how to structure the sequential processing of the elements, the images, and the pages, and so on. So take a careful look at this code. and you can kind of see what the overall logic is. Now that we've walked through the sequential loops crawler implementation, let's turn our attention to sequential streams crawler. As you can see, this class is an implementation of an image crawler that will use Java 8 sequential streams to obtain, transform, and store images. Let's take a look at the perform crawl method first. I give you the implementation of this method. This method will recursively crawl the given page that's passed as a parameter, and it will return the total number of processed images reachable from that page or on that page. Taking a look at the implementation, you'll see a parameter called depth is passed in, and we compare depth to see whether or not we've reached the depth limit of the crawl. You can set the max depth limit by the app in its setting menu. And if you've exceeded that, then we return 0 because we don't want to crawl indefinitely, especially if there's cycles in our crawl graph. The next thing we do is we check to see whether or not we've already visited this page URI before. And if we have not visited it, we atomically add it to the mUnique URIs map. Or actually it's a hash set, so we don't try to revisit it again unnecessarily. We don't want to end up double counting these links and recursing indefinitely because we have loops and cycles in our call graph. And the last thing we do, we're going to call a helper method called call page, and that will recursively crawl all the images and hyperlinks on this page, returning the total number of processed images. So here is crawl page. The implementation, which you will have to provide using Java 8 sequential streams, will use Java 8 features to download and process images on this page via process image, and recursively crawl other hyperlinks accessible from this page via perform crawl. So it's going to end up calling back recursively to this method up here. And of course, it'll do that whenever it reaches something that's actually not an image, but in fact, a hyperlink. And when it's all done, it'll return a sum of all the image counts, either images that were on this page or images that were accessible via hyperlinks on this page. Now, to figure out what you actually have to do here, you go back over to sequential loops crawler and you take a look at the crawl page method here. And this implementation gives you the code, except it uses Java 7 control constructs like a for loop and if-else statements. But your sequential streams implementation should use many of these same elements. It's just going to use the streams framework and the aggregate operations therein to control the flow rather than using loops and if-else statements. So you'll have to take a look here and kind of see how this is going to work. It's really quite cool. So if you go back over here, you can see that one of the things you need to do in crawl page is call process image. You can kind of see that over here. You can see that if you've got an image, you call process image. If you have a page, you call perform crawl. And that's the same thing you do here. You just have to do it with Java 8 streams. So let's take a look at the process image method that you have to fill in. This is going to process an image at a given URL by applying any transformations that have not already been applied and cached. So let's first go ahead and take a look at how that works for the sequential version using loops. And as you can see here, this will loop through all the transformations in the mTransforms list, and it will attempt to create a new cache item for this transform. But it'll only apply the transform if the new cache item was actually created. In other words, we're not going to do this if we've already cached the solution in an earlier run. So create new cached item, takes an image and a transform, and it returns true if you need to actually apply the transform. It returns false if it's already there. So down here you can see we will call apply transform, passing in the transform and the image, and then we increment the image count by 1. And that image count is what's returned as the result of the process image method. So that's how it works with loops and if statements. So your implementation, conversely, has to work without loops and without if statements. So you'll have to use a stream, and you'll convert the transforms list into a stream, and then you'll go ahead and do the other logic that is necessary in order to make this all work properly. So you'll have to kind of figure out how to do this, and you'll also have to figure out how to transform and store each non-cached image. And so you'll use things like map, and you can use other methods like filter and so on. And when you're all done, you'll return the count of transformed images. And that, of course, will be the same result you had earlier, except if you had done it with the loops version, except you will have computed it using streams. So that's basically the logic that you'll have to implement here. And so I recommend you watch the videos, obviously come to lectures, come to office hours, ask lots of questions. This is not a particularly hard assignment, but if this is your first time learning streams, it takes a while to get your head around how the various pieces all fit together. Now that we've discussed the specification and walked through the skeletons, it's time to run the unit tests and see whether or not the implementation works properly. As usual, you'll come up here and you right-click in the image crawler source test Java folder and click on Run All Tests. As you can see, we have quite a number of tests here. We have 100 tests altogether. These tests test all kinds of different characteristics. They test your sequential streams crawler. They'll also test the synchronized array for the grads. They'll test the unsynchronized array iterator and unsynchronized array splitterator. And then there are lots and lots of tests for the unsynchronized array that you wrote for earlier assignments. Keep in mind that we keep adding new tests as we get better insights as to what the frequently made mistakes are. So something that might have worked earlier may fail because our tests are more extensive. As you can see here, for this particular implementation, which is my master implementation, all the tests work properly, which is good news, which means you can actually implement this stuff to work and pass with flying colors. So please make sure you run the tests. If you run into problems running the tests, don't hesitate to come to office hours or post on Piazza or ask questions in class, because chances are if you're running into problems, other people may be as well.